So we're going to start with oxidation-reduction reactions, which are more formally known as redox reactions. So you might ask what a redox reaction is. Well, it's not when the captain brings the boat back to a pier, contrary to popular belief.
A redox reaction is more formally known as an oxidation-reduction reaction. It is a type of chemical reaction that involves the transfer of electrons. It is any reaction in which a species' oxidation number changes. In a redox reaction, one species must lose an electron in order for another species to gain an electron. Reduction is any chemical reaction that involves the gaining of electrons. Thus, the reduction reaction is the reaction in which a species gains an electron. The flip side of this is oxidation. An oxidation reaction is one in which a species loses an electron, thus changing its oxidation number.
A good way to remember this is by thinking Leo the lion says grr. So Leo stands for losing electrons, oxidation. And grr stands for gaining electrons, reduction. Now that we have covered the basics of what reduction and oxidation are, we can discuss what a reducing agent and oxidation agent are. A reduction agent is one that loses the electron in order to have a reduction reaction. Without this agent, reduction would not happen. An oxidation agent is one that gains an electron, thus causing an oxidation reaction. If there wasn't an oxidizing agent, there would not be a species to accept the electron lost by the species that was oxidized. You can think of them as secret agents in a way. Hi, the name's Agent, oxidation agent that is. I'm on a mission to find an electron. I've been told there's another agency looking to dispose of one. Let's hope we're successful today.
Hello, I'm with the reduction agency. I'm the top agent looking to dispose of this electron properly. I've been told to look for this agent in green. Wish me luck.
You from the reduction agency?
Who's asking?
I think you know. You got the electron?
I got it.
That was a way of showing the transfer of the electrons. When the reduction agent had completed their mission, they had gotten rid of an electron, and when the oxidizing agent had completed their mission, they had one more electron than when they started. There are redox reactions happening around you all the time, a few examples being iron rusting and the oxidation of the Statue of Liberty. When iron is rusting, it is a reaction between oxygen and iron. The oxygen is being reduced while the iron is being oxidized. This means that the oxygen is gaining electrons, making it the oxidation agent, while iron is losing electrons, making it the reduction agent. The Statue of Liberty is made of copper, however, it is a blue-green color. Why is this? This is also due to a redox reaction. The copper that the statue is made of is oxidized by the oxygen in the air. In this reaction, the oxygen is the oxidation agent, while the copper is the reduction agent. This is due to the fact that the copper is losing electrons while the oxygen is gaining electrons. This reaction is what caused the blue-green color that you now see on the statue. Now you might be asking yourself, what is an oxidation state? Well, lucky for you, we were about to explain that.
Now we're going to discuss oxidation states or numbers. These are a number that is assigned to an element, ion, or part of a compound. So we have a few different examples here to show you. Usually when an element stands alone, actually always when an element stands alone, it has an oxidation state of 0. Now, if it's an ion, it's going to have either a positive or negative oxidation state. In this example, we used sodium, which will usually have a positive 1 oxidation state number by itself in an ion form. Next we have a compound, NaCl, or sodium chloride, which is table salt. And we have a positive and a negative oxidation number. Now chlorine, because it's in the halogens, will have a negative 1 oxidation state number. And sodium is in the alkali earth metals and will have a +1 oxidation state number. And they make a neutral compound together because the oxidation state numbers equal 0 when they're added together. Now we're going to talk about water, which contains oxygen and hydrogen, which usually will have the same oxidation state numbers. Oxygen is generally a -2 oxidation state number, and hydrogen is usually +1. In this example, we have 2 hydrogens, so you're going to multiply the +1 by 2, get a charge of +2, and then you add that to -2 and get 0, so water is a neutral compound. Now we will teach you a critical skill in chemistry, and that is balancing redox reactions. There are three main ways of balancing a redox reaction: simple, bridge method, and ion-electron method. With the ion-electron method, it can be done in either acidic or basic solution. We will start with simple, and it's often how you go about balancing any other reaction, looking at it and seeing what needs to be balanced. So, looking at this, you can see that copper has a 2+ charge, and silver only has a 1+ charge, which means that you need 2 silver to balance out the charge. But since you added 2 silver here, you also need to add 2 silver here. And the copper balances out, so this would be a simple way of balancing a redox reaction. Now we are going to show you how to balance redox reaction using the bridge method. The first step would be assigning oxidation numbers, which we already did. Now you're going to look to see which ones have a change in oxidation number. In this reaction, it's the Mn, which goes from +7 to +2, and the As, which goes from +3 to +5. So what you're going to do is draw a bridge connecting them. And then you'll look to see what the effect was on the electrons. Now here, you had a gain of 5 electrons, so you're going to write +5e-. And here, you had a loss of 2 electrons, so you're going to write -2. And now you'll determine what number you have to multiply each by in order to get an equal amount of electrons. In this case, we'd have to multiply the 5 by 2 and this by 5. So that means that you're going to have 2HMnO4 because you multiplied this whole molecule by 2. And then you'd have 5Na3AsO3. And you wouldn't change the HNO3 because the oxidation numbers didn't change in that. And then once again, you'd have 2 and then NO3 plus 5H3AsO4 plus NaNO3. Now, you're just going to check to make sure that you don't have any issues with. And then after inspecting the equation, we balanced everything by mass. And this one was a bit complicated, so we didn't want to just completely bore you to death. So here's what the final equation would look like. We will now show you how to balance a redox reaction using the ion-electron method. And this can be done in both acidic and basic solution, where the first 2 steps are the same. But after that it changes. So our first example is an acidic solution. So here we have our net ionic equation written out, along with the oxidation numbers. From here you can determine what your reduction and oxidation reactions are. So the reactions here are Cu solid yields Cu2+, and NO3- yields NO. Now here's when you would balance anything besides hydrogen and oxygen. Since we don't have anything that needs to be balanced, we're going to go straight to balancing the oxygen. So we don't have any in our copper, but we do have 3 and 1 in this equation. So what you're going to do is write NO3- yields NO, and then add the number of water molecules that you need in order to balance the oxygen. So that would be 2 in this case. From here, you'll balance the hydrogen. So you have no hydrogen on this side, and you have 4 on this, so you can write 4H+. From here, you'll figure out the charges of each side. So in this equation, we have a 0 on this side and a +2 on this side, which means we need 2 electrons here. And that's that equation. And here we have a +3 charge and a 0 charge. So that means we need 3 electrons here. And that's that equation. Now, in order to balance the equations, we're going to multiply this by the number of electrons that we added in this equation, and this by the number of electrons we added in this equation. So that'd be multiplied by 2 here and 3 here. So we have 3 Cu solid plus 6 electrons plus 8H plus 2 NO3- yields 3 Cu2 plus 2 NO plus 6 electrons plus 4 H2O. Now what we're going to do is cancel out anything that repeats on both sides. So that'd be both of these, and then you look to see if anything else cancels out, which it doesn't. So your final equation is 3Cu solid plus 8H plus 2NO3 minus yields 3Cu2 plus 2NO plus 4H2O. And from here, I'm just going to add the charges quickly to make sure that they add up. So here we have plus 8 and minus 2, and that equals 6. And here we have plus 6, so they are balanced, and this would be your final reduction reaction. Now we're going to show you how to balance a redox reaction using the ion electron method in basic solution. Now it's very similar to acidic, but there are a few slight variations. So first you have your ionic equation, and now you're going to write out your half reactions. Now this is where you would balance anything that's not hydrogen or oxygen, and as you can see in this example, everything besides the oxygen is balanced. So what we're going to do is add water molecules to each side to balance the oxygen that is necessary. So in this reaction, we have 4 oxygen on this side and 2 on this, so we're going to need to add 2 water molecules. And in this reaction, we have 1 on this side and none on this side, so we need to add 1 water molecule. Now, from here, we're going to add the hydrogen to try and balance out the hydrogen. So we have 4 on this side, so we're going to add 4H plus here. And we have 2 on this side, so we're going to add 2H plus here. And now you're going to add OH minus to each side as many H pluses as you have. So we have 4 here, so we have 4 OH minus plus 4 OH minus plus 2 OH minus. Okay, so now the OH and the H plus can become water molecules. So here we have 4 H2O plus MnO4 minus yields MnO2 plus 2H2O plus 4OH minus and 2OH minus plus H2O plus Cn minus CnO minus plus 2H2O. So now we're going to cancel out the water molecules where we can. So we can make this 2 and get rid of them on this side, and we can make this 1 and get rid of it on this side. So So now this is where we add the electrons to try and balance the solution. And so we have a -1 charge here, and a -4 here, and a -3 here, and a -1 here. So since there's that difference, we need to add 3 electrons to this side, and we need to add 2 electrons to this side. So now we're going to do our multiplication again. So for this, we're multiplying it by 2, and this we're multiplying it by 3. So we have 6 electrons plus 4 H2O plus 2 MnO4 minus. And then I'm going to take the other half reaction, like the forward reaction here. So plus 6 OH minus plus 3 Cn minus yields 2 MnO2 plus 8 OH minus plus 3 CnO minus plus 3 H2O plus 6 electrons. And now we will cancel out anything that we can. So we can cancel out the electrons on either side. We have 3 water molecules here and 4 here, so we can make this 1 H2O and get rid of this H2O. We have 8 OH here and 6 here, so we can get rid of this and make this 2. And I believe this will give us our final reaction of H2O plus 2MnO4 minus plus 3Cn minus yields 2MnO2 plus 2OH minus plus 3CnO minus. And now we're going to double check our charges. So we have minus 2, minus 2, well, minus 2, minus 3, so this would be minus 5, and minus 3, minus 2, minus 5. So the charges equal each other, so this is our final reaction.
Now I will show you how to use an activity series in order to determine in which way a redox reaction will go. The complicated thing with redox reactions is that the water can also be reduced or oxidized, which is why I use an activity series in order to determine which reaction is more likely to occur. An activity series gives you the reduction potential of a half reaction, where the equation that is the most positive is the most likely to be reduced, and that the lowest reduction potential is the most likely to be oxidized. Enthalpy is the heat absorbed or released under constant pressure. Heats of fusion, vaporization, etc. are usually given as enthalpies. They can be looked up in tables such as this one. Enthalpy is a state function. A state function is a property of a system depending on its condition or state, basically its endpoints, and not its history or path. We care about how it started out initially and how it ended up, not how it got there. Enthalpy is a state function because in transforming reactants into products, the change in enthalpy is the same, whether the reaction takes place in one step or a series of steps.
We are now going to show you how to calculate enthalpy using the heat of formation. Now, each one of these has a different heat of formation. And in order to calculate the total reaction heat of formation, you would do the products minus the reactants. So you're going to do 3, because we have 3 of the H2O molecules, and then that's negative 393.509 plus 2 times 24183 minus Now the heat of formation for a solid element is always going to be 0, but you should write it in just then you know that you accounted for it. And your total heat of formation here is negative 1,428.66 kilojoules. Yeah.
Entropy describes the randomness of the universe.
Okay, maybe not that kind of randomness. The kind of randomness that describes the disorder of the universe. To understand entropy, we need to understand spontaneity. Spontaneity is the ability to occur without outside intervention. Spontaneity has a definite direction. If a reaction is spontaneous in one direction, it won't be spontaneous in the other. Temperature must play a role in spontaneity. For example, water becoming ice in the freezer where it's 0 degrees Celsius is spontaneous, but water becoming ice on the kitchen counter where it's about 24 degrees Celsius is not. A reaction is spontaneous only if it's exothermic and results in a favorable change in entropy, meaning the products are more disordered than the reactants. It must also be irreversible, meaning the process of the reaction cannot be reversed to restore the system to its original state. That requires a different path and a change in surroundings.
Now that's an irreversible reaction.
When we talk about entropy as the randomness or disorder of a system, it is also a state function. Here we notice that spontaneity involves an increase of entropy in the universe. Reactions with large negative enthalpies seem to be spontaneous, and spontaneity is related to entropy and enthalpy. That's why we have Gibbs free energy, a new state function related to enthalpy and entropy that gives us a way to predict whether a given reaction occurring at a particular temperature and pressure will be spontaneous. For a system at equilibrium, delta G equals 0. We can use recorded thermodynamic data to calculate values for standard free energy in any reaction.
We're going to use this equation to calculate the Gibbs free energy to see if this reaction will be spontaneous. So, delta G will equal 1 kilojoules per mole minus, and then multiply temperature standard our final result would be that the free energy is equal to 173.3 kilojoules per mole. And because we have a positive delta G, we know that this reaction is non-spontaneous. If we had a negative delta G, then this reaction would be spontaneous. We're going to be calculating the free energy under non-standard conditions. When we produce ammonia with the Haber process, this is the standard free energy, but we're not at standard conditions, so we're going to have to do a separate calculation. So the standard, we're going to convert it to joules so that we can keep the same units throughout. It's going to be negative 33,330 joules per mole. Add it to constant. At our temperature, 400 Kelvin, and our LNQ, which in a separate calculation we found out that Q is equal to 0.00926, and so we just do the math from there, find out that our non-standard delta G is equal to negative 48.9 kilojoules per mole. We're going to be calculating the equilibrium constant using delta G. We're going to be using for the same equation when we produce ammonia with the Haber process. So our K would equal e to the negative. The standard delta G's we calculated before was negative 33.3 kilojoules per mole divided by 8.314 times the negative third, because we wanted to use the same unit, kilojoules. And that's going to be multiplied by our temperature, 98 Kelvin, and our final K comes out to 6.87 times 10 negative.
Let's talk about electrochemistry. Electrochemistry is the study of relationships between electricity and chemical reactions, since energy released in a spontaneous redox reaction can be used to perform electrical work. The flow of electrons is an electric current and can be used in many useful applications, such as batteries, fuel cells, the plating of metals, and combustion.
We're going to be studying electrochemistry through the little battery that could. We're not doing the little battery that could.
Why not?
Because it's stupid and it's not the best way to explain electrochemistry.
But I made the costume.
This goes so I can talk about voltaic cells.
Fine.
A voltaic cell is an electrochemical cell used to convert chemical energy into electrical energy, in which the transfer of electrons occurs through an external pathway rather than directly between reactants. This is what occurs on a microscale in a battery. Nope. We're good.
A voltaic cell is made up of two half cells, consisting of a piece of metal submerged in a solution of its ions, where either the oxidation or reduction half reaction will occur. The salt bridge is a tube containing a strong electrolyte, an ionic compound whose ions will not react with the other ion solutions of electrode materials in some kind of gel, allowing ions to travel between the half cells without allowing the solutions themselves to mix. An electrode is the metal strip or wire in a half cell that functions as a conductor in a circuit that carries electrons to or from a substance. The anode is the electrode at which oxidation occurs, and the cathode is the electrode at which reduction occurs. One way to remember this is an ox and red cat.
To show you how a voltaic cell works, we're going to make our own. That does not mix batteries. So to make our voltaic cell, we have a piece of copper in copper sulfate and a piece of zinc in zinc sulfate. And we connected them with a sodium sulfate bridge that we made by soaking a piece of paper in a sodium sulfate solution. Now we attach our electrodes to each. Let's see if we get a positive or negative voltage. We're getting a positive voltage, so we connected them correctly. Now right now zinc is being oxidized, so it's our anode, and copper is being reduced, so that is our cathode. Electrons are produced at the anode as products of the oxidation, so the metal at the anode will become smaller as the reaction proceeds. Right now, the zinc metal is losing mass. The electrons leave the anode and pass through the wire to reach the cathode. Once electrons enter the cathode, they will interact with the ions in solution on that side. There, electrons are gained by the ions, and the reduction caused them to become metal, which plates to the cathode metal. Right now, the copper metal is gaining mass. To complete our circuit, cations move through the salt bridge towards the cathode, where there's an excess of negative ions in solution, and anions move through the salt bridge toward the anode, where positive ions are being produced. As we can see with the blue strip in our salt bridge, a lot of the ions have indeed moved.
These reactions in voltaic cells are spontaneous because they're based off of a difference in potential energy. Their potential difference, or the difference in potential energy per electrical charge between the two electrodes, is known as the voltage. 1 volt is equal to the potential difference required to impart 1 joule of energy to a charge of 1 coulomb, a unit of charge. We call this driving force that moves the electrons through the circuit the electromotive force, or EMF, or cell potential, or cell voltage. The electrical potential, or cell potential, is the measure of a voltaic cell's ability to produce an electric current. A cell's electrical potential results from the competition for electrons between the two half cells. The half cell that has the greater tendency to gain electrons will be the one in which reduction occurs, and oxidation will occur in the other half cell. We can tell which half cell will reduce or oxidize through an element's reduction potential, or the measure of its tendency for a half reaction to occur. These values are found in a standard reduction potentials table. It is important to note that a spontaneous reaction will result in a positive cell potential, while the non-spontaneous reaction will result in a negative cell potential.
Non-spawn.
Can't stop it.
Wait, you can't stop it?
It's not my code. My code doesn't work.
You're right, your code doesn't work. Stop the code to my phone. And now we're going to show you how to calculate the cell potential of a redox reaction using a standard reduction potential table. The reaction we're going to do is the lab that we showed you earlier using copper and zinc. So our reduction half reaction was copper 2 plus 2 electrons equals copper solid. And so that's a standard reduction potential of 0.34. So you're going to write 0.34 volts. And then we have to find our oxidation half reaction, and that was the zinc. So it was not zinc 2 plus 2 electrons make zinc solid, but it was zinc solid is going to form 2 electrons in zinc 2 plus in solution. So instead of having a negative 0.76 as your reduction potential, you have a positive 0.76 as your oxidation potential. So you're going to add that to the 0.34. And that equals 1.10 volts. And as you recall, the number that we got on our voltmeter was about 1.05 volts, which is very close to what the actual cell potential is. So I would say it was a pretty successful experiment. The opposite of a voltaic cell would be an electrolytic cell, where 2 electrodes in a molten salt or solution are driven by a battery or another source using electrical energy to make a non-spontaneous reduction reaction occur. Keep in mind, an, ox, and red cat still apply. An electrolytic cell can have many purposes, such as the plating of metals and jewelry. So in this lab, we currently have 2 pieces of copper foil in a copper solution. If you look at the solution, you can see that the copper ions are transferring from one of the pieces of foil to the other, more so. Keep in mind that the foils can't touch and that you need to keep this at a certain... Are you touching? Okay. So we're going to show you how to do an electrolytic cell calculation. And so our question was to calculate the number of grams of aluminum produced in 1 hour by electrolysis of molten AlCl3 if the electrical current is 10 amperes. And remember that coulombs equals amperes times seconds. So we had 10 amperes times 3,600 seconds is 36,000 coulombs, and that's where we're going to start. to show you how to figure out the equation of a molten salt breaking down. So you're going to separate it into the two half reactions. So Na plus makes Na. We have to add one electron here. And then F minus goes to F2 because it's a halogen. So you need to balance this with 2F2 and add 2 electrons. And to balance out the electrons, you're going to multiply this one by 2. So you get 2 Na plus 2 F minus makes 2 Na plus F2.
When we're with aqueous salts, we also have to think of water. If the cation is harder to reduce than the water, or the water is more easily oxidized than the anion, then we're going to use the water in the reaction instead. So here we have our example using copper and bromine. And so we see for the copper, it has a higher reduction potential than water, so we're going to use copper in our reaction. And bromine would have a higher oxidation potential than the water. So in this case, we would use them both, but just keep in mind that you will have to pay attention to the oxidation and reduction potentials, just to see if water would be used in the reaction.
No.
Fine.